So here's a brief overview of all of the data that we have for CephC and about what I mean when I say band merging, and also some common misconceptions I'll cover at the end. So what data do we have? We've got lots and lots of data already. We have lots of images, and from those images we have photometry, in other words, quantitative measures of the brightnesses of the sources in those images. We have images that cover many different wavelengths, and not every source is detected in every image. So every survey is integrating for a different length of time, and so the faintest sources they reach are different, not just because of the different exposure times and the different telescopes and the different detectors, but also because the objects themselves have different brightnesses over this wide range of wavelengths. And the issues of resolution are really important for us because, when I say resolution, I mean how close do two sources have to be before we can't distinguish them as two sources. And we're going to have this problem in spades with the data that we have. So here's a table of the existing data that we have. We're really basically going to ignore the X-ray data. I don't think there's much that we can do with it right now. There's Sloan data, which is optical in the bands U, G, R, I, and Z. There's pan-stars, which are G, R, I, Z, and Y. IFAS is R, I, and H alpha. 2MASS is J, H, and K. It's starting to move into the near-infrared. Spitzer is mid-infrared and starting to go into the far-infrared, so between 3.6 and 70 microns, although I don't think we're using any 70 microns from Spitzer. There's many different sets of data from Spitzer, so that may be somewhat confusing because there's cryo-era Spitzer, which has all of the available bands, 3.6 to 70 microns. But there's, after we ran out of cryo, only the shortest two bands of Spitzer continued to operate, and there's two additional sets of data that used Spitzer, the shortest two bands on this region. One is GLIMPSE, which is a survey of the galactic plane, and the other is YSOVAR, which was monitoring this region at those two shortest IRAC bands. WISE is 3.4 to 22 microns. That was an all-sky survey, but not as sensitive as Spitzer is. On the other hand, there's WISE data all over the sky. That's the trade-off. Then, of course, the heart of our project is the Herschel data, which is far infrared between 70 and 500 microns. There's SCUBA data, which is ground-based at 450 and 850 microns. You will really see the difference in sensitivity between the ground-based SCUBA and the space-based Herschel. I already talked a little bit about the YSOVAR data, and then there's a handful of objects that were identified as H-alpha bright stars. So that's narrowband photometry, just at 0.656 microns, and there's only two sources in this region that were called out by that larger survey as being particularly bright in H-alpha. So we have, by my count, 38 different bands and or times of observation. I think I counted YSOVAR as just one in this context because YSOVAR, of course, observed this region many times over the period of 40 days. So I think I just counted the YSOVAR as one net. And then the photometry is done for nearly all of them. We've got some Herschel photometry, but we're going to have to do some Herschel photometry. So in terms of what the data look like, so I've got a whole stack of screen snapshots here. They're all from my view of DS9. I've changed the aspect ratio so that it fits on the screen better. I put the banners on the side. But all of the images that I have here are lined up on the screen to each other, so they're all covering the same chunk of sky. So this is Sloan U, G, R, I, Z. And so you can start to see, as we go into longer wavelengths, more and more stars are detected. If I go back to U, there's not very many stars that are detected. And by the time I make it to Z, there's lots of stars detected. You can make 3-color images, which sometimes help you see those differences. So this is using R, I, and Z for the RGB planes. I guess it's BGR because R, in this case, the band R here would be the shortest wavelength, so that would be mapped to blue, I is green, and Z is red. So you can see that the hearts of these stars are not necessarily white, right? So that they're not the same brightness in all three of those bands. And here you can start to see this sort of V or Y-shaped nebulosity that we're going to become very familiar with as we go to the longer wavelengths. So there's pan-stars. Now, pan-stars covers the whole region, but the tiles they offer don't. So this is, again, the same chunk of sky, so we're kind of off the edge of this particular tile, but the data do actually exist. So G, R, I, Z, Y. So same sort of thing. When you get more, they go to longer wavelengths. Here you get more stars. So there's a 3-color image with I, Z, and Y. Now we have DSS. Now we don't have any photometry from DSS, nor do we want photometry from it. This is scanned photographic plates. But because Finder Chart accesses the DSS images, we can still use it as part of our image inspection process, even if we don't have any photometry from DSS. So there's the blue photographic plate, another scan, red, and blue, and near infrared. So it's the same idea. Longer wavelengths have more stars. Then we have 2 mass J, many stars, and you can also see that this is it's a mosaic of smaller tiles. You can see sort of the patchwork quilt effect. That's H, where the patchwork is even worse. And then there's K, many stars here. And that's the pretty sad 3-color view, where really what dominates things is the patchwork quilt problem. But you can start to see that the center has really red stars, and all of the point sources out here are blue. That means that they're brightest, those outer bluer stars are brightest in J, and then these stars in here that are red are brightest in K. All right, so now we're moving into more space-based data. We've got IRAC 1, 3.6 microns, WISE 1, 3.5 microns. Look at how the resolution is different and the number of sources detected is different. That's because IRAC is higher spatial resolution and IRAC is more sensitive. So there's more time that went into the IRAC frame than in the WISE frame, and the telescope is more sensitive for Spitzer than for WISE. But the but look, the Spitzer data has an end to it. WISE data doesn't. That's just a tile chunk taken out of the all-sky survey. This jagged edge, those are the individual frames that went into mapping this region. So IRAC 2 and WISE 2 has the same sort of thing. More stars, higher resolution for IRAC than for WISE. IRAC 3, now we're starting to get into some more interesting features here. For the first time in a while, the longer wavelengths we go to is fewer stars, not more stars. This is 5.8 microns, and you can start to see the nebulosities becoming more interesting. There's bright nebulosity and there's dark nebulosity. 8 microns. Okay, still lots of dark stuff, even at 8 microns, and fewer stars than there were at 5.8 microns. Okay, there's a 3-color image using just IRAC data. Now, WISE 3 is 12 microns. So poorer resolution, but also fewer stars, and the nebulosity is becoming more and more prominent. There's 22 microns and 24 microns, so that's WISE, that's Spitzer. Here again, MIPS, just like IRAS, higher spatial resolution and more sensitive. So you can see sources more easily in MIPS, and they go fainter. But we're still going to use the 22 micron stuff because there's still interesting information there that can be used. This is PAX 70, so this is the first of the Herschel data. Look how many fewer stars. Even at, so if we go back all the way to 5.8 microns, there's a lot of stars. Fewer, skip the color, that's fewer. That's got a little bit more because it's more sensitive than 22 microns. But look how many fewer stars are at 70 microns. Part of that is that the emission from most of these stars is plummeting as you go to the longer wavelengths. If the stars don't have dust around them, that's just going to plummet like a black body shape. And Herschel is phenomenally sensitive, but these are very long wavelengths. So even though Herschel is a big telescope and very sensitive to these wavelengths, they're still not detecting very many sources in this region. But the sources that are detected here are likely to be the very interesting young stars that we're looking after. There's 70, there's 160. So here it's mostly the large-scale emission. There's not a ton of point sources. That's trying to combine 24 micron from MIPS, the 70 micron from PAX, and the 160 micron from PAX. Here again, the nebulosity is bright in the red because it's attached to the longer wavelengths. And the blue is the shortest wavelengths here. So there are some sources that are only blue. They're not detected at the longer wavelengths. So there's Spire 250. Now that's mostly nebulosity, though there are point sources in there. Spire 350. Spire 500. Look how the pixels are getting bigger. When you go to the longer wavelengths, it's because the resolution is getting worse. So they didn't bother making a detector for Spire 500 that had pixels as small as they do for 70, because why would they? The resolution of the telescope's getting worse. So here too, there's not a ton of point sources. 250 micron has some clear point sources. 350, 500, really hard unless you know going in where the point sources are. So that's a 3-color image with just the Spire data. Now the scuba data is really weird because it's ground-based, and so the way that it is, the data are obtained and calibrated are completely different than in space. So you have to fiddle with the stretch differently, but this is on the same scale as the other ones. So this bright region that is right here is that region, and there's more things that you can see in the 850 micron, but it's ground-based data, and it's just not as sensitive. So there's a huge amount of data. How can it be that no one's worked in this region before? Well, there's several reasons for that. One is that this is part of the galactic plane, and there are many different galactic plane surveys. So our region has been hit accidentally, serendipitously, by these surveys, but nobody spent a lot of time going after specifically this region. There, a handful of observations that I just showed you were taken deliberately of CephC, but no one has yet published them. And so for some of those data, as long as it's public, we've snarfed them up. So the team last year and you guys are really the first ever to care a lot about the individual sources in these data. And because this field is so complex, we're going to have to spend a lot of time untangling what's going on. So things that you can think about before you get here in the summer is looking at how Pan-STARRS GRIZ compared to Sloan GRIZ. So Pan-STARRS has an additional Y and Sloan has an additional U, but GRINZ should be awfully similar, if not actually the same filters. So how do the images compare? Which one is deeper? Which one sees fainter sources? And you can do the same thing looking at IRAC 1 and 2 and WISE 1 and 2. Very similar bands, not the same, but very similar. How do they look different? And the same for MIPS 1 and WISE 4. We talked a little bit about that, but you should get in and play with the images themselves so that you really understand what that means. And just as a reminder, for some of those frames that I showed you, the data seemed to end. Like for Pan-STARRS, it's just a piece of the tile, but there are more Pan-STARRS data that we've grabbed. I just didn't grab the images. But in other cases, it really is the edge of the data, like the Spitzer data stops. So, of course, not all of these images are the same integration time. Not all of them reach the same sources. Not all of them reach the same fluxes. And they're definitely not all the same resolution. So this is why you guys are doing this. If they were identically assembled and completely immaculate, then I could just write code to do this. But that's why you guys need to be involved. That's why it takes people to solve this, because these images are very different and the resolutions in particular are very different. So on the topics of photometry and band merging. So remember, photometry is the quantitative measure of the brightness of an object in any given band. We've got lots of photometry that's been done for us, and so we've got lots of data already, but we have to band merge it. Band merging it means merging the catalogs across the bands. So some catalogs arrive to us already merged. So for example, the 2-mass survey has J, H, and K bands, but because that one survey was doing all 3 of those bands, they have already merged that for us. So for each line in the 2-mass catalog, it has a measurement at J, H, and K. That doesn't mean it's detected at all. It might be a limit at J and H and a detection at K, for example. But at least there's one line per source with the measurements at all those bands. The WISE catalog similarly has one line per source with all 4 of the WISE bands. But those 2 catalogs are not merged together. So we need to figure out which 2-mass source corresponds to that WISE source. And that's going to be the case, linking together all of these things. So Pan-STARRS has already merged their sources. Sloan has already merged theirs within their catalog. The Herschel data, what we have, is not merged. So it's going to be, even though we've got like a catalog of Pax fluxes, we've got a catalog that is, just one per each of the bands that we have. We have an additional complication for what we're doing because we're going to have sources that break into pieces. There's going to be something that looks like one source in the Herschel bands that breaks into 2 or more pieces at the shorter bands. And we're going to have to figure out how we can, if we can, apportion the flux correspondingly. So we're going to, the goal of band merging is to create a catalog where there's one line for each unique object in the field and collect all of the wavelengths on the same line. So you can kind of think of it as a baseball card, right? So there's one line or one card for each source, and all of the information we know about that source is collected in that line or on that baseball card. We're going to need to do this in order to make color magnitude diagrams and SEDs. So that's why we're doing this. And as I keep saying, not all catalogs see the same objects, not all surveys go to the same depth, and the objects themselves are changing with wavelength. So the code that I've written that I'm going to use on your behalf is that what it does is for each catalog, for each object in the catalog, it sits metaphorically on one object and looks for other matches in the other catalogs within a certain radius on the sky. So for example, 2-mass and WISE coordinates are really good. So for each 2-mass source that I have, I say, okay, is there a match in the WISE catalog within 1 arcsecond? If there is a match, great. I can combine that information. But if I didn't find one, then it becomes more complicated. Is 1 arcsecond the right radius to use? For 2-mass and WISE, yes. But when we get to different surveys, that maybe that's not the right radius. And what are the uncertainties in position? Because, for example, the scuba positions are not only fairly uncertain, but probably the uncertainty changes with position on the map. So that's going to be hard. And if we find more than one source within, so if I go between 2-mass and WISE, if there's 2 sources at 2-mass that are within 1 arcsecond of the WISE position, is the source, those 2 sources at 2-mass really matched to the 1 source at WISE, or is there something else going on? And does the resolution matter in that case? And what are the positional uncertainties? And there's going to be judgment calls in that process. So this is just a picture of what that process looks like for the catalogs that I've already assembled. So the green here is our nominal region of study, and all the black crosses is right ascension and declination in decimal degrees. And so all of those black crosses are individual sources within the 2-mass catalog. And so you can start to see that V or Y-shaped structure where there's no sources because it's obscured for 2-mass wavelengths. So then I'm going to combine the 2-mass data with the cryo data. So I ended up, because the cryo data is incorporating data from a couple different exposures, there are more sources in this rectangle that comes basically from the IRAC coverage than the MIPS coverage, which is larger, and there's fewer sources that are detected. And so you can see already that not every instrument is detecting the same density of sources. But each one of those red diamonds corresponds to a source in the Cryo Spitzer catalog. And then when the diamond is right on top of a cross, then that's a match. You can see that there's places with less sources, but in the middle now it's already become complicated to see which source goes with which, but the computer keeps track of that. Now I'm going to add in the glimpse data. You can see I asked glimpse for a larger region than we cared about, but again, there's lots of sources that match. Now the black crosses are everything we've done so far. That's the existing catalog. And then the red is Sloan data. So you can see that there's Sloan counterparts for lots of things out here, but there's holes where there's no Sloan data because there aren't any sources. And these bizarre strings of sources are probably not real. They're probably sources that appear only in Sloan and don't have counterparts. And so they're going to get dropped by the next step. So this is the catalog. I've added now everything in black has everything that I've assembled so far. Now the red on top of it is the IFAS data, the RI and H alpha. Now we're going to add in the WISE data. Now we're going to have the scuba data. So remember the scuba data, there's only 16 sources, and so those are the 16 sources. So in the end, then, in that green square that we care about, there's 17,000 sources that have detections at least one band. But it's important to know that not every one of those 17,000 sources are detected at all bands. And those 17,000 sources are everything in the catalogs. Probably has nothing to do with CephC, particularly. Be foreground, background, okay? So it's just everything in this region. So it's not just the young stars, it's everything in that region. So last year's team, which was the Llama team, I put a banner on the top that's going to carry forward so you can remember which things I'm talking about specifically pertain to the 2016 NITARP team called Llama. They started from the 17,000 sources, and they let the computer pick things that it thinks are young stars. And it did that in several different ways. The first way was it said, okay, which ones have IRAC colors that make this object look like a young star? This is otherwise known as looking for IR excess, or the Rob Gutermuth approach. In order to do that, it requires 4 bands of IRAC and 3 bands of 2MAS. And so remember that not everything meets that criteria. There's plenty of things that might be missing 1 band of IRAC. It might be missing not because it's faint, but because it's bright, it's saturated, and so there's no measurement from IRAC. It's not using any optical information or any longer wavelength information. It's just IRAC and 2MAS. And so remember that the IR excess is coming from the circumstellar dust around it, either a disk or a shell. And there's plenty of things that are seen in all the IRAC bands that are not young stars. So of that entire catalog, those, that is just 2MAS plus the cryo Spitzer. Those red dots are those IR excess identified sources. You can see there's many, many fewer in that green box than there are sources. So the next thing was which ones of all the sources in this region are bright in H alpha, because the young stars, if they're actively accreting, should be bright in H alpha. Or if they're rotating quickly, like many young stars do, they should be bright in H alpha. So in order to do that, you need to have detection in IFAS, which I guess I didn't include in the images that I had put in the PowerPoint above. So that one, remember, IFAS is an RI and H alpha survey, which is all optical bands. In order for it to come up as bright in H alpha, it requires detection in all 3 bands, which not every object meets. And it's not using any infrared. It's not using any other optical. It's just RI and H alpha. It's not a very deep survey, and there's plenty of things that are seen in all 3 of those bands that are not young stars. So there's really only 4 sources that show up as bright in H alpha, only 2 that are in the region that we care the most about. So the third criteria that Llama used to identify young stars is variability. So we've got these YSOVAR light curves. Which ones are variable? Because the young stars are going to be variable. Turns out quasars are also going to be variable, and sometimes older stars can be variable, but young stars are typically quite variable. So in order to identify them as variable, it means they have to be detected in those images. And we looked both for long-term over years variability and short-term over hours, days, or weeks variability. Note that this is not over hundreds or thousands or even tens of years, and it's not over milliseconds. So it's hours, days, and weeks to years. So when I say LC, it's light curve, and it's the brightness measured over time. Not everything has a light curve. It's not, when I look for variability in the YSOVAR data, I'm not using any information from any other bands, and there's plenty of things that have light curves that are not young stars. The 4th criteria is which ones are detected in X-rays. Because the young stars, if they're young enough, they're rotating quickly, they should be very active, and so they're bright in X-rays from flares. In order to do that, it means that the objects have to be detected in X-rays, and there's plenty of things that are not detected. And in addition, we have to have enough other bands to be able to tell that the SED looks more like a star than it does an AGN, an active galactic nucleus, because AGN are also very bright in X-rays and can have a lot of infrared. So we don't have a hard requirement that it needs to be detected in, say, all 4 bands IRAC. We just need to have enough detections to see what the SED shape roughly looks like. So there's plenty of things that are detected in X-rays that are not young stars. So from that 17,000 sources, they came out then with 300 candidates that met one or more of the 4 criteria of IR excess, H-alpha excess, variability in the YSO of our data, and X-ray detection with a young star-like SED. So then for each one of those 300 sources, they looked at the images in the SEDs and decided to throw out about 50. So they kept 250 that they thought were probably young stars. Now we're going to come in. So the biggest thing that Llama didn't get to do was work with any wavelengths longer than 24 microns. Herschel's got 5 bands we can work with, and Scuba has 2 bands, but is much less sensitive because it's ground-based. So the Llama team started looking at the Herschel data, but decided it was too complicated to go on, because Herschel has many different resolutions and sensitivities and coordinate uncertainties and much higher backgrounds, which means it's harder to see the sources. And at the time they were working on it, there wasn't any photometry that was already done. Now we have some preliminary Spire photometry and we have some PAX photometry. So we will try and match those in where we can and do the photometry that we need to for the remainder of the sources, because they didn't go any further with that. The Llama team didn't go any further with that. So that's where we're coming in. So some of their 300 sources are detected by Herschel, but many sources detected by Herschel are not on the original Llama list because it didn't meet any of those 4 it didn't meet any of those 4 criteria for finding young stars. So there's 17,000 sources in the region. The 2016 team worked with one subset, and we're going to work with another subset. Some of our sources are going to be the same. Some of our sources are going to have young, light curves, but not all of them will. And this is just, again, repeating that they weren't on the list before because maybe they didn't have any detection at shorter bands, or maybe it didn't have a light curve. So Herschel doesn't see, you can see in those images, it doesn't see a lot of point sources. And the things it does see are pretty bright, which probably means they're close, which probably means they're young stars in CephC. Only the most embedded young stars are going to be very bright at Herschel bands. And no one, to my knowledge, has looked at these data in any detail. And I'm pretty sure there's some interesting sources in there that we're going to find. So we need to get the photometry for Herschel. We're going to leverage all the data we already have. We have all these other data, and the closest wavelength that we have, which has lots and lots of point sources that are very well detected, are the 24 micron image, and there's something like 300 sources in there. So we're going to start with that list, and we're going to see if we can find matches in the Herschel data. And from looking at those images before that only some of those 300 are going to be detected. But we're going to find them. We're going to find the matches. So we're going to some extent, let the computer do the photometry, but we're going to do some photometry by hand to make sure that we understand what's going on. We're going to have to check each source by eye to make sure that we believe that it's a real source. And we're going to spend some time trying to figure out what source that all of these Herschel sources should be matched to at the shorter bands. And we're going to assemble the SEDs with all the data that exist that we can assemble. And then we're going to make color, and color magnitude diagrams to try to figure out if we can learn anything about what these sources are. So possible misconceptions or confusions you might have. Class 0 objects, which are the youngest of the young stars, are glowing from thermal emission. So their SED looks like a black body. We're looking at the cocoon of dust re-radiating the radiation from the protostar. So the SED looks like a cool black body. As the YSO ages and the cocoon dissipates, we have a much better look at the central object, which is a lot warmer now than it was when it was completely embedded in the cocoon. The dust near it is still heated up by the star or the young star and re-radiating in the infrared. So some of the SED is going to come from the young star and some of it is going to come from the dust around it. And so there's going to be a warm black body for that central star, and then probably not necessarily something that you can represent as a single black body at the longer wavelengths. When you have still older young stars, you may have a much more tenuous disk or even a ring. So in those cases, you can kind of treat it as all the dust is a single temperature. So then you have a warm black body from the young star and then a cooler black body from the dust. So remember that spectral energy distributions are not the same as black bodies. Some of the SEDs resemble black bodies or can be approximated by single black bodies or sums of black bodies. But SEDs are not the same as black bodies. The words are not interchangeable. I don't know why when I teach this, there's this confusion. If I knew why, I'd teach it better. But you just have to remember that SEDs are not the same as black bodies. Some of the things we will see, I think, are going to be class 0, so they're going to look like cool black bodies. Some of the things we're going to see are going to be older, so less embedded. And some of the things we're going to see are going to be complicated by the fact that we've got emission coming from the central source and emission coming from the dust cocoon. And so that may make a difference, and it may mean that the SEDs are harder to interpret, but we got to make the SEDs before we decide that that's a problem. So just to remember, this is the last slide that I have, and you can see the banner at the top reminding you these are Llama SEDs. These are the SEDs that they picked to go on their final poster. So you can see the diversity of data that we have. And there's energy density as a function of wavelength. So you can see all the optical data. And then here, this one has a big honking disk. This one probably has a smaller disk, right? This one has a smaller disk. This one probably has no disk. Now look, not all of them have optical data. Lots of optical data there, none there. Optical data there and there, but none there. Not all of them have long wavelength data. Here we've got lots of MIPS and Ys, MIPS and Ys, MIPS and Ys. No MIPS, no Ys. MIPS and Ys. So this is what we're going to have too. We're going to have objects that don't have long wavelength data, objects that do. We're going to have objects that don't have optical data, and objects that do.